Now that we've talked about solutions and how we can measure their concentrations in a variety of ways, and we've talked about some properties, we're going to talk about colligative properties, which is a variety of properties that specifically depend on the quantity of solute that you put in, but not the identity of the solute. So some of these colligative properties are vapor pressure lowering, boiling point elevating, freezing point lowering as well, or they call it freezing point depression, and then osmotic pressure. So starting with vapor pressure, we want to talk about what is vapor pressure again. So vapor pressure happens when we have an equilibrium of solvent molecules escaping into the vapor phase at the same rate that vapor molecules are recombining with the liquid phase. And we get this equilibrium pressure, and it's related to how strong the IMFs are for that solvent. So when we have weak IMFs, we get a lot of molecules in the vapor phase, high vapor pressure. When it has strong IMFs, not as many. So now if we add a solute, well, in order to create a solution, that solute has pretty strong IMFs with the solvent. And so this is like a strong magnet, and it's holding molecules in the liquid phase even more. So now we're not going to get as many escaping into the vapor phase, and more molecules are then going to be stuck. So we create this new equilibrium where we have less molecules in the vapor phase than we did with our initial solvent. So that has to do with our solution. So when we have a higher concentration of our solute, specifically non-volatile solute, meaning it's not going to create any vapors, it's going to make it harder for our molecules, our solvent molecules, to escape into the vapor phase. So therefore, the vapor pressure is lower than of its pure solvent. It could be related by Raoult's law, which says that the new vapor pressure of the solution is equal to the mole fraction of our solvent, that's important, times the initial pressure of our pure solvent. So if I just have a pure solvent, no solute, then the mole fraction of the solvent equals 1. So now once I make a solution, mole fraction is going to be less than 1. And if it's a solvent, it is the majority. So that means it's going to be between 0.5 and 0.1. And generally it's going to be around the 0.9-ish region. And it could be a little higher, a little lower, but that's a pretty general good range that you'll see your mole fraction in. If you see it less than 0.5 or greater than 0.1, you know you did some kind of calculation wrong. So let's practice. If I have glycerin, it's a non-volatile, non-electrolyte. So we're going to start to notice when we see non-electrolyte, that means that if I dissolve it into a solvent, it doesn't break into ions. So that means that its I equals 1. We're going to talk about I soon, but I is basically how many particles did it break into when it dissolves. So all non-electrolytes or molecular compounds will be 1. Now it has a density, glycerin has a density of 1.26 grams per milliliter at 25 degrees Celsius. Calculate the vapor pressure of the solution made by adding 50 milliliters of glycerin in 500 milliliters of water. And it says the vapor pressure of water at this temperature is 23.8 torr. And its density of water at this temperature is 1 gram per milliliter. Okay, so we want to find the vapor pressure of my new solution, and that's going to be equal to the mole fraction of our solvent, which in this case is water, times by the vapor pressure of water. So we need to find the mole fraction, of water. That was weird. Okay, so let's find mole fraction of water. Remember, mole fraction of anything, in this case water, is going to be the amount of moles of water divided by the total moles. So in this case, water plus moles of glycerin. So let's find out how many we have. We have 50 milliliters of glycerin, and 500 milliliters of water, and we need to find the moles. So I'm going to try to get to moles. So how can I get out of milliliters? So you maybe think I need to go to liters, but this isn't a concentration, this is a pure substance. So I'm going to use, here we see density has units of grams per milliliter. So I'm going to plug that in for glycerin, 1.26 grams per milliliter. And for water, 1.0 gram per milliliter. Now I'm in grams, so now you should be familiar. Going to moles, we're going to use a molar mass. So the molar mass of glycerin is 92.09 grams per mole. And then for water is 18.02 grams per mole. So after calculating it, I get 0.684 moles of glycerin and 27.7547 moles of water. So then I could plug that in up here. I put the 27.747 moles of water divided by 27.747 plus 0.684. When I calculate that, my mole fraction, which I'm going to just plug in up here, is 0.976. Then I'm going to take that and multiply it by my pure vapor pressure of water, 23.8 torr. So I get a new vapor pressure of 23.2 torr. So we can tell it dropped. So let's try it again. I have, and this is a more, like, to me, a more fun question because it's a little bit more interesting. So now I know the vapor pressure of benzene is 100 torr at 26.1 degrees Celsius. So assuming that we could use Raoult's law, how many moles of a non-volatile solute must be added to 100 milliliters of benzene? So I have 100 milliliters of benzene. Oops. And to decrease its vapor pressure by 10%. So if I was at 100, now I'm decreased by 10%, so now I'm at 90 torr. So 90 torr equals my mole fraction of benzene times by 100 torr, my original one. And so now I can find out, okay, my mole fraction, I'm going to solve for that. So I'm going to divide by 100 torr on both sides, cross out. So I now know my mole fraction of benzene equals 0.9. Well, we know mole fraction of benzene means moles of benzene divided by moles of benzene plus my moles of solute, which we don't know. That's what we're going to try to find. So let's find moles of benzene. I have 100 milliliters of benzene. I know the density of benzene, so I can find out how many moles of it I have. I have, so 0.8765 grams per milliliter. Remember, a centimeter cubed is a milliliter. And now I can go from grams to mole. So the molar mass of benzene is 78.11 grams per mole. So I have a total of 1.122 moles of benzene. So I'm going to plug that right here. So now I'm going to do cross multiplication because I want to get x on top. So let me actually move this guy over. I'm going to do something real quick. Let me pause and clear my screen. Okay, so I am going to say 0.9. Whoops. I'm actually just going to cross multiply. So I'm going to switch my denominator with my other side. So I have 1.122 moles plus x equals 1.122 moles divided by 0.9. And then I'm going to move this guy over by subtracting 1.122 moles. So now I have x by itself. So I'm going to do this calculation, and I get the amount of moles of my solute, x, equals 0.1247 moles. Okay, so since it takes a lot more, since our vapor pressure is lower for my solution, so if here is my vapor pressure to boil, remember to boil something, I have to get my vapor pressure up to atmospheric pressure. So if I'm at sea level, I'm here. Now if I make my solution, my vapor pressure is lowered. So I'm not at sea level, or I'm not at atmospheric pressure yet, so I need to actually heat it up. I need to add more energy. So I have increased my amount of temperature that it requires to boil. So I'm going to boil at a higher temperature now because I have to heat it up more to get it up to atmospheric pressure. So boiling point is raised. Now at freezing, we are going to see a freezing point drop because now that I have created a solution, those IMFs are stronger for my solution than they were in my solvent, so it actually takes more energy to get those solvent molecules to stop moving around and stop being in solution and just be frozen. So my freezing point will drop, it'll go down. So now basically I have a bigger temperature range where I am in a liquid phase. The calculation that we will use to find the change in temperature for boiling and freezing is given here. So it is proportional to molality. Whoops, we're going to want to use molality because we're having so much temperature change. We don't want a change in volume to be a factor. So it's going to be related to how many particles a substance breaks into when it dissolves, or the Van 't Hoff factor I. So for molecular compounds like sucrose, sugar, etc., I equals 1. When I'm dealing with something like NaCl, I have 1 Na, 1 Cl, so I have 2 particles, so I is 2. When I have something like calcium chloride, I have 1 calcium, 2 chloride, so I is 3. So we're going to say, how many things do I break into? So the relationship is the change in temperature of boiling point equals the Van 't Hoff factor times my boiling point constant, which is specific to my solvent, times the molality. For freezing point, since I'm going down, I'm going to have a negative I times the freezing point constant, again here, times the molality of my solution. So let's practice. If I have an automotive antifreeze contains ethylene glycol, a non-volatile non-electrolyte. Now you see those non-electrolyte and you think, ding, 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 that means I don't break into ions, so I equals 1. Calculate the boiling point and freezing point of 25% by mass solution of ethylene glycol. So, delta T, delta TB and delta TF, I'm going to write the equations. So I KB times molality and negative IKF times molality. So we need to find molality. Molality is moles of solute over kilograms of solvent. So we don't have molality, we have percent mass. So if I have 25% mass of ethylene glycol, that means I have 25 grams of it in 100 grams. So I'm just going to say 25 grams of ethylene glycol. Now my molar mass of ethylene glycol is 62.03, or I'm just going to put 62 grams per mole. So we're going to find those moles. I'm also going to say if I have 25 grams of ethylene glycol, then that means I have 75 grams of water. And I need to turn that into kilograms because that's my solvent. So I have 1,000 kilograms, 1,000 grams per kilogram. So that's 0.075 kilograms. So let's find the moles. I get 0.403 moles of ethylene glycol. So I'll plug that in. 0.403 moles over 0.075 kilograms. And that gives me, my molality is 5.376 molal. So I'll plug that in. Now I, for both of these, is 1. So I'm going to multiply 1 by 5.3, whoops, I lied. We want to do K first. It doesn't really matter, but we'll just be consistent. Now K for water, KB for water is 0.51 degrees Celsius per molal, and for KF is 1.86 degrees Celsius per molal, times by my molality, which is 5.376. And so I can calculate that now. So times by 0.51. So my boiling point is going to raise by 2.74 degrees Celsius. So I now need to add 100 to that because that's my boiling point at sea level. So my new boiling point is 102.74 degrees Celsius. Now for my boiling point, my freezing point, I have 1.86 times by 5.376. So I get that to be 9.999, a lot of nines, degrees Celsius, negative. So that means I need to add my freezing point, which is 0. So conveniently, it's negative 9.999 degrees Celsius. Basically, negative 10 degrees Celsius. So notice, freezing point's a lot more impacted than boiling point. Okay, now a fun way to do it. I have an unknown, non-volatile, non-electrolyte. I equals 1. Was prepared by dissolving 0.25 grams. So my mass of my unknown, or my solute, I'll say, be specific, solute equals 0.25 grams. And I have dissolved it in 40 grams of carbon tetrachloride. So that's my mass of my solvent is 40 grams. And the boiling point of the resulting solution was 0.357 degrees higher than a pure solvent. So delta TB equals 0.357 degrees Celsius. So calculate the molar mass. So I know delta TB equals I KB times molality. So for carbon tetrachloride, if we look back on the last slide, the KB is 5.02. So it's a non-electrolyte, so I is 1. 5.02 degrees Celsius per molal. Times by molality, we don't know. And my delta T is 0.357. So I'm going to solve for molality. So I'm going to divide both sides by 5.02. And I get my molality is equal to, let's find out, 0.357 divided by 5.02. My molality is 0.07112 molal. And that's equal to moles of solute, which we don't know, divided by kilograms of solvent. But I know grams of solvent, so I'm going to convert that into kilograms by dividing by 1,000. So I have 0.04 kilograms of carbon tetrachloride, and I don't know my moles of solute. So now I have 0.07112 molal equals X over 0.04 kilograms. So I'm going to times by 0.04 on both sides to get X by itself. So 0.04 times by 0.07112 equals, so X, or my moles of solute, is 0.00284 moles. Now, molar mass is what we're finding, and that's grams over moles. So my grams that I added in my solute was 0.250 grams, and I have 0.00284 moles. So if I just divide those two numbers, I get my molar mass equaling 87.89 grams per mole. So basically, we experimentally can know how much we put in. We can then measure the boiling point change and then find out how many moles that should equal with this equation, and then calculate grams that we added divided by moles we solved for to find that mass. And you did that in lab. Okay, the last property we're going to talk about is osmotic pressure. So sometimes we have substances that can move through a semi-permeable membrane. So that's a membrane that allows small particles to pass through, but large particles are blocked. And generally we think our solvent as being small, and water is pretty small, and our solute as being larger. So we end up getting movement of solvent molecules from low concentration to high concentration across this membrane. That's called osmosis. So here we have solvent on the right side or left side, and a solution on the right. So our solvent's gonna move over. As it does, our volume raises. So the osmotic pressure is how much pressure we have to add down to get those molecules to, or those levels to even out again. And that pressure is the osmotic pressure. This has an equation of pi being osmotic pressure. So P for pi is the Greek letter for P, and we do that for pressure, equals I, the Van Hoff factor, times molality, times the gas constant, times T. So the R here that we're dealing with is 0.0821 liters atmospheres per mole Kelvin, and our temperature is in Kelvin, and this is molarity, so mole per liter. So the average osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius. What's the molarity? That will be isotonic with blood, so same concentration. So pi equals IMRT. So I'm going to plug in 7.7 atmospheres equals 1, glucose is a molecular compound, times molarity, times R, times temperature. So 25 degrees Celsius, we need to get it in Kelvin, so add 273, and I get 298 Kelvin. So I'm going to divide that over. So molarity equals 7.7 atmospheres divided by 0.0821 per mole Kelvin times 298 Kelvin. Notice atmospheres cancel, Kelvin cancels, and then liters per mole is on the denominator, so it will flip up, and what we get is 0.315 molar. Which of these actions will raise the osmotic pressure? Decreasing the solute will lower the concentration, which will lower the pressure. Decreasing the temperature will lower the pressure. Adding more solvent will lower the concentration, which will lower the pressure. And increasing the temperature, raising temperature should raise it, so D. Okay, when we have osmosis, we have to have two different types of concentrations. So we're always going to be comparing one thing inside another, and they're separated by that membrane. So isotonic means we have the same concentration, so we're going to have the same osmotic pressure. So basically, I'm going to have molecules flowing out at the same rate that I have solvent molecules flowing in. So they're happening at the same rate. So we get this really nice balance. When I have a hypotonic solution, hypo means low, so I have lower osmotic pressure. So basically here I have this low solute concentration, so now I have extra solvent, so it's going to flow in more, so I'm going to actually expand my system here, and I'm going to, so solvent's going to be leaving the hypotonic, so here I'm going in, and so I'm going to end up getting something where my system gets bigger. If my system's in a hypertonic solution, that means high concentration, so I have a higher osmotic pressure, so solvent will be entering. So what happens here, if my high concentration is on the outside, then my extra solvent is inside and it's going to flow out, so my system will actually end up shrinking. So when we have red blood cells, they have semi-permeable membranes. So if they're in the hypertonic solution, then they're going to have a lot of water leave, causing the cell to shrivel. And that is called crenation. If I put a cell in a hypotonic solution, then all of that solvent will enter until they burst, and that's called hemolysis. So it's really important when you have IV solutions that it is isotonic with the blood. So it's more than just putting medicine in water, it's really making sure that you have the right osmotic pressure. So a fun type of question with osmotic pressure is, again, finding the molar mass of an unknown solvent. So the osmotic pressure of an aqueous solution of a protein was measured to determine the protein's molar mass. The solution contains 3.5 milligrams of the protein dissolved in enough water to form 5 milliliters of solution. The osmotic pressure of the solution at 25 is found to be 1.54 torr, treating the protein as a non-electrolyte, so I equals 1, calculate its molar mass. Okay, so we have a lot of info, but we know we're using osmotic pressure, so we're going to use that equation. Pi equals I m r t. And I know pi is 1.54 torr, so I need to get this in atmospheres. So I'm going to divide by 760 to get that into atmospheres. So 1.54 torr divided by 760 equals 0, I'm going to do it in scientific notation, 2.03 times 10 to the negative 3 atmospheres. Oops. That equals 1 times the molarity. I don't know that. R is 0.0821. And my temperature is 25 Celsius. So just like the last problem, it's 298 Kelvin. So I'm going to find molarity. I'm going to take that number and divide by 0.0821 and 298. So I get my concentration equals 8.28 times 10 to the negative 5th molar. So we know molarity is moles of solute over liters of solution. Now I know my solution was 5 milliliters. So I'm going to find how many liters that is. So I'm going to divide by 1,000. So that is 5 times 10 to the negative 3 liters. So that's what I'm going to put on my bottom. So I have 5 times 10 to the negative 3 liters. So I'm going to solve for moles, which is x. So I'm going to multiply both sides by 5 times 10 to the negative 3. That cancels out. So my moles of solute equals 4.14 times 10 to the negative 7 moles of solute. Now remember, molar mass is grams per mole. And know my moles. Bring that up. 4.14 times 10 to the negative 7. And I'm going to take I had, 3.5 milligrams. So 3.50 milligrams. Now I need that in grams. So I'm going to divide. I have 1,000 milligrams in 1 gram. So that is 3.5 times 10 to the negative 3. So I'm going to put that up top. And I'm going to do 3.5 times 10 to the negative 3rd divided by my answer, but divided by 4.14 times 10 to the negative 7. And I get my molar mass of my protein being 8.45 times 10 to the 3rd grams per mole. Now proteins are really big, so that makes sense that it would have a really large mass. Okay, last section is on colloids. So this is a type of solution where we don't get things completely dissolving, but rather they stay as a particle. So they're larger than ions because ions completely dissolve and are really small, but are so too small to be able to settle out by gravity. So this is called a colloid. The colloids are unique because if I shine light through a regular solution, the light passes straight through. It doesn't interact with the particles in there because they're so tiny. But with colloids, the particles are large enough that the light actually scatters, and this is called the Tyndall effect. So that's what we see happening here. Now we can have lots of different types of colloids with different phases. The only one you can't have is a gas and a gas because you won't be having particles large enough to do Tyndall effect. And this is because a gas inside a gas is always homogeneous, so this is always a solution. But here we see gas, liquids and solids and gases, gas through solid and liquids, and gas through solid and solids, all creating different types of colloids. So take a peek at that and be prepared to think about some of those properties.